we are talking about lighting model in OpenGL. So, lighting is one of the principal part in OpenGL, like texturing, or we have vertex transformation. Lighting is also highly important. It makes a kind of a scene realistic, like people feel that model is illuminated in a light source. So lighting is important in OpenGL. When we see lighting, there are three components in the light. One is light source that emits the light. Material, actually we are looking the material, not the light. So light source, material, and then our eye. Our eye watches material. Light falls on material. Material reflects the light and it comes to our eye. To get better illumination, light must fall on the surface in perpendicular way. If light and surface are parallel to each other, then surface won't be visible nicely. If light falls on surface at 90 degrees, then surface would be illuminated to its maximum strength. So, light source falling at what angle on the surface, and surface is at what angle to the eye. Light has three parts: its position, its direction, and its color. Okay. So in lighting model, when we talk about the light, material, and camera eye, then for the light we talk about its position. So light may be at infinite far away, like sun, or light can be nearby, like bulb light or candle light. So that is called a positional light. So type of the light: light position, light direction. In what direction light is to the surface? So we don't call it that light should fall on the 90 degree at the surface. So every surface has its normal. So light should be in parallel to the normal. In mathematics, light direction and normal, if we make dot, then it should be 1. So that is the idea. Now when light reflects from the material, it falls on our eye. So three things in light model: light position, light direction, and color. Okay. So position can be infinite away, position can be nearby, positional light. Light direction, light must be in direction from at the normal of the material. And light color. So light falls on material, material reflects the light, and reflection should come to our eye. It should be in this position. Now, once we talk about light, color, and material reflection. So material should, if material, the nature of the material reflects the color, what it is. If material is green, then it reflects green color. If material is blue, it reflects blue color. If material is mixture of green and blue, so that one it reflects. So let's consider material is green, then it reflects green. Light must have green. If light is red, then material has nothing to reflect from the light. So if light is red, falls on a green material has nothing to, it absorbs the red light and it tries to reflect green, which it doesn't have. So it looks black. So if I have a white light that has red, green, blue, all three, then green material would absorb red and blue and it would reflect green. And it falls on our eye and we look at it look green. So that is the concept of coloring. So three things as we talk: position of the light, direction of the light. Direction of the light, it should fall directly on the material in the sense that it should fall at the 90 degree at the material, or should be parallel to the normal at the material, and material should reflect the light. Once it reflects the light, then it should fall on the camera. Okay. Now be more realistic in the OpenGL. OpenGL is like in the smooth shading model. OpenGL is like a vertex manipulation. OpenGL doesn't think much about all the pixels and light falling at which pixel and light not falling at which pixel, color at which pixel. So this computation doesn't happen in OpenGL. All calculation happens for the vertex. If I have a triangle and in the triangle I have 3 vertices, calculation will happen at 3 vertices only, not the thousands of pixels in between. So if light position matters from the vertices, light direction matters from the vertices, reflection happens from the vertices, and then it falls on our eye. So whatever computation we make, then that computation finally comes to the pixel. That is called fragmentation or rasterization. So in OpenGL we provide vertex coordinates, we provide vertex color, but in lighting model we take away the coloring. We provide material properties like ambient or like diffuse, like a specular. So these are the property that we provide. So main property is diffuse property. So if we provide diffuse color at the vertices, that is the color. So light, once it falls on the vertices, then vertices reflects its diffuse property light and it falls on it. So, two things we talked about. One is general concept of a light, like its position and its direction and its color. This is the general tradition. If a ball is green, light must have green component. Light must fall on the ball and in the direction, and ball must reflect the green component to the eye. So this is normal tradition. In OpenGL, we have to consider only vertices. So what is the vertices normal? So that light should be in parallel to the normal, and when it reflects, where is the camera? So in OpenGL, we take care about the vertices. Next thing what we take care in OpenGL is model view matrix. So we have three matrices: projection matrix, model matrix, and view matrix. So what do we see? That the model must be inside the projection box, and from a view perspective, generally we keep the view fixed. So if model has a transformation, then finally we see from the view or from the eye what is the final transformation, and that we try to show it. So model inside the projection box comes to the view. What about lighting? What about the light source? If light source light position is declared after the model view matrix is defined, then it follows the transformation. So we can also rotate the light source, we can also translate the light source like this. So two things special. One thing we talked about natural lighting, that is position, direction and color of lighting. Material reflects a particular component of color, it falls on camera or eye, that is the natural. In OpenGL, whatever computation we do, we provide vertices, we provide normal, we provide coloring of the vertices through diffuse. So vertices computation happens in OpenGL. And next is that light is also subject to transformation. It can also rotate, it can also translate. If position is defined, position is placed in the source code. After we load the model view matrix, we place identity matrix, then it is also subject to transformation. If it is before it, then light source is fixed. If it is after, means if it is along with the model and we start translating or doing the transformation, then it would also transform. If we don't want transformation, it should be declared before the view matrix is declared. Okay. If we declare the light source after the view matrix and before any transformation, it won't transform. It will be static. As we keep any one. So this is the lighting modeling. Okay. So we'll see through further how it is.
In continuous OpenGL fixed function pipeline. So we'll proceed and test. This is reenactment. We'll proceed point by point. OpenGL lighting model. Lighting model is important everywhere. So we'll see lighting model that is implemented in OpenGL, and it's feasible, it's workable. So what is the mathematics behind the scene that we'd see? OpenGL lighting model constitute light source, mainly RGB we'll talk about, material reflecting light RGB to the eye. So light source and material. So OpenGL in lighting model, it supports RGB and color index. So we'll discuss about RGB. For GL smooth shading model, only this is what we are talking now. And vertex has to receive the lighting. Vertex has to receive the lighting. No explicit per fragment pixel calculation. Means lighting calculation has to happen at the vertex. Kind of a fragment shader in the shader. But anyway, we are not discussing about shaders now. Light source position set after view matrix is subject to transformation. So if light source is set after view matrix, then like a model is transformed, rotated, scaled and translated. So light source can also be rotated, translated in that manner if it is position is set after view matrix is set. Light reaching to the eye or camera depend upon the light source property, like what is position, direction and color. So these three things are important things. And this is, it follows transformation if it is declared position is set after the view matrix. For the GL smooth shading model, vertex has to receive the lighting. And RGB, light is emitting RGB color, material reflecting RGB to the eye. And it supports RGB and color index model. So RGB, that we'll see. Okay, so we'll see lighting type. There are two types of lighting. One is directional light and one is positional light. Directional light is a light that is kept infinite away. Like here, it is kept in plus z direction, infinite. So the light that comes is parallel. So shadows are parallel. Light comes from infinite distance. Like here, this is plus z axis and this is minus z axis. So light is going towards minus z axis from plus z axis from infinite distance. There is no position here. I cannot say that light is kind of, this is the starting point. So there is no position. So from infinite position in z direction, it is going in minus z direction. So this is directional light, whereas positional light or point light, It is also called point light. So point light, it is placed at one location and kind of in 360 degree, the way any light is, like a bulb, that it emits light in all direction. So in 3D all direction. So light is kept at a position. So this is a position. This is a position, and around it light is being emitted. This is positional light. Whereas this is directional light. It is coming from infinite point to a direction, minus z direction, and parallel lights. Certainly this is not a parallel light. Okay, so light source can be made a spotlight by placing a cone. Like if I have a positional light and I am placing a cone. So this is one side of the cone and this is another side of the cone. Okay. So this is one side of the cone and this is another side of the cone. So this is a cone. Light that is inside the cone, that only propagate, otherwise these areas there is no lighting. So this is called spotlight. So spotlight is also famous, means also possible, I would say. So this is parallel light, directional light, point light, positional light. If I place a cone, I can make it as a spotlight. So I have to set some property and it becomes a spotlight. I have to mention the angle in the spotlight. Okay, so as discussed, if I have like this is a pyramid, one side, next side, and this side. This is the base. This is a pyramid. For the pyramid, these are the vertexes. This is a vertex. This is a vertex. And this is a vertex. This is a vertex. Light must fall on the vertex. Light may not fall on the surfaces. Not required. So, vertex, if we see without lighting, we specify the vertex coordinate and vertex color. Instead of vertex color, now it will come as material properties. So, light must fall at the vertex. Whatever the light color falls at the vertex and whatever the property of the material is, that point will carry that light. Then it will span over all the area in the surface. So, in a smooth model, if this is red and this is green, then in between this area would be yellow. So light must fall on the vertex. This is a big point. Light position for the directional light in the direction. Okay. So in directional light, if I set light position, so position of a light, this is 0, 0, 1, 0. Okay. Whereas for the positional light, this light position, so positional light, if I set light position 0.8, 0.2, minus 1.2, that is the position of the light, not the direction. If I set the fourth parameter as 1, so this becomes a positional light. So whatever the coordinate I am setting, these coordinates are position of the light, and light would be is kind of omnidirectional. In all directions it would propagate. But if it is a directional light, last parameter would be 0, argument would be 0. So claiming it is a directional light, and whatever we are placing 0, 0, 1, it shows that direction of the light. So 0, 0 means x is 0, y is 0, z is 1. This is 0, 0, 0 origin. This is the direction we are talking about. 0, 0, 1. This is z is 1. in this direction at infinite distance, light is placed. Okay. So, if I say light position is 1, 1 and 0, means x is 1, y is 1 and z is 0. So, it is positioned in xy plane, that is 45 degree in xy plane. So, that would be in this direction. So, if I say okay, so this is the origin and this is z axis. Okay. Now, if I say light position is is 0, 1, 1, 0. So, fourth parameter say is a directional light. So, 1, 1. So, if I see the vector, then, okay, if I see the vector, then this is 1 x-axis in this direction, one y-axis in this direction, both are 1, means it will go in 45 degree from x-axis and y-axis. So, light is in this direction and the angle is this. So, this angle is 45 degree. Okay, so since it is a directional light, so light in this direction, light is actually, it is placed somewhere far infinite in this direction. So actually light is coming in this direction. If light position says 1, 1, 0, 0, 1, 1 is this, z is 0. At infinite distance, light is placed. Since light is placed here, it is pointing in reverse direction. So, in this direction. So, this is directional light source. So, if I say light position in 1, so somewhere on z axis light is placed. Since light is placed at infinite distance, light is pointing in this direction. Whereas in positional light, whatever the position we are setting, light is positioned at that direction and omni way it is just emitting the light. Okay, so what is light emission and reflection? So this is a lighthouse and it has a color called 111. So it is kind of emitting a white light. So this is a white light. R is 111. Now, this is light emission from the light source and this is a model. This model has a color is 010, so red green, so it has a green. What it does is it absorbs red and blue. Since it doesn't has a red, it doesn't has a red and blue component. So R and B gone. G has 1.1, so it reflects green. This guy, since it does not have blue, and red, so whatever blue and red component comes, it reflects. So whatever blue and red component comes, it absorbs, and green it reflects. So even though the light coming is white light, only green is coming out. We can set this as 0.5. Then green will green will come out, but intensity would be less. We can come to a formula in this. Okay, so the formula would be for this is L light red into material red plus light blue light green into material green plus light blue into material blue. So this is the actual reflectance. This is the reflectance formula what this material support. So light is 1, light red is 1, material red is 0. So no lighting, no red. Light blue and material blue, same way material blue is 0. So there is nothing. Okay, so light and material, so only this part LG and MG, light green and material green, this is only will come into the picture. That's why it looks green. Okay, now it is 1 into 1, this is 1 and this is 1, so it would really look green. Here it is 0.5, though it is green, but intensity would be less. So this is the mathematical calculation for the lighting. So the material color reflects its light, absorbs other part. Okay, if light coming is red, no green and blue, then there would not be any lighting at all, because LR is 1 and LB is 1, sorry, light is red, LR is red, LG and LB are 0, means these are 0, and MR is 0, so there won't be any lighting at all. So this is mathematical formula of lighting. In physical way, material reflects its color, absorbs other color. Lighting means in addition to RGB color, lighting has other component also. So if it is a if light is coming from a light source, it has ambient part, it has diffuse part, it has a specular part, and in similar fashion, in material also there is a diffuse part, specular part, shiny, specular, shining is part of a specular, and ambient. Okay, so ambience is kind of environmental light. Suppose there is no lighting. Suppose there is no lighting. If there is no lighting, then what would be the light of the material? Okay, so I am inside a room and there is no direct lighting. Lighting are through reflections from here and there and whatsoever. What would be the ambience lighting? So light source can add to ambience. And there is another guy called light model. Light model also adds to ambience. So ambience factor is a light that a material would show if there is no lighting. So that is the ambience light. Like here, this is the front light, but back side there is no lighting. So whatever we see, I think it's a kind of a greenish black. It's not pure black. It's a greenish black. So this is the light on back side. It is showing if there is no lighting. This lighting is depend upon the light model. Light model is another entity that we can add, we cannot add. It is up to us. So if we enable light model, and light model, if we change the ambience, so light model light model is available, and light model we can kind of add in light model, add or delete, in the sense that ambience of the light model we can change. So if by default ambience of a light model is something, I think 0.02. So light model ambient and ambient of the lighthouse and ambient of this material, all three comes to make a ambience of the material. Likewise, diffuse, likewise specular. So diffuse is the actual color of the light. Ambient is the color of the environment, the way the name is ambience. If there is no lighting, like backside of, typically if we have a lighting, what would be the backside lighting when there is no lighting? That is the ambience. Diffuse is the front light. What is the actual light that is thrown from the light source? So similar diffuse, so these are reflectance. If actual light is coming, so whatever we talk now, this is diffuse one. Whatever we see, it is diffuse light. So lighting is actually diffuse light. Out of all the lighting component, what we talk is light coming from a light source is diffuse light. Ambience make important if other side of the area in the material where light doesn't come, it should still show some color. This is the main light, diffuse light. Specular light is the place where light falls at 90 degree of the surface or in the parallel to the normal. There should be shining also. So that is called a specular component. All component follows this principle only, RGB, and this multiplication, all component. So these are different component of the lighting. Ambient, what would be the lighting of the material where there is no lighting. Diffuse is the actual light, and specular is the where the light falls directly, like here. Light falls directly at this part. So here there will be shining. Otherwise it will be like this. What would be the specular component? What would be the shining color? And what is the color, shining color that is coming from the light source? So that also we can define. So light source is saying that if I fall directly on the material, then it should shine like this. Well, this is the OpenGL calculation method. Ambience makes sense, and diffuse also makes sense, but light source also identify that if light falls on material, then please calculate through specular component. And material also, so generally it is white because shining will be white. So that is the idea. So light has three component: ambient, diffuse, and specular. Ambient is if there is no light, then what the calculation will be. Diffuse is the actual light, and if light falls directly on the surface, what would be its shining color? So these are light component, and these are materials reflectance component. How much it would reflect? Like in this example, it is reflecting what, only 0.5. It is reflecting green, but only 0.5. Here it is reflecting green and full. So material, whatever material we have, all are reflectance kind, all are reflectance parameter. Whatever we have in the line, that is the actual light parameter. These two will get multiplied and in the direction of the camera eye. Finally, it will come to the actual lighting. Light follows model view transformation matrix. Like if camera is here, at 0, 0 camera is here. Okay, so I think we can add. So if camera is here, Okay. If camera is here and we can see this model is placed, it is placed inside a projection box, and if light is position is defined after the light model position declared after model view transformation matrix load identity. Once we load the identity, then it is subject to transformation. If light is here, now light is here, that's it. Light can move the way model moves, the way model translate, rotate, and so the scale. So scaling cannot happen, but translate and rotate whatever we see, so that it can also follow. So this is the transformation. This is the transformation, means light also follows if it is position is defined after the view matrix and load identity is calculated. So this is about lighting. Okay. So there is a mathematics. So what would be the actual color at the vertices? So we said that the lighting calculation happens at vertices. So what would be if light has ambient, diffuse and specular? If light model has ambient and material has these many reflectance, what would be the actual color at the vertex? Material has also one part called emission, material emission, like what light it emits, like a kind of a light source. But it won't be that much bright, but its own brightness. So vertex color would be the material's emission. Ambience, light model into ambience material, like this, whatever calculation we made. LR, MR, and so whatever is ambience at the light model and material model. So this RGB. So ambience of the light model. So light model is external light, we can say. This is light source. This is light model. Light model is kind of external source. It has many other properties also. So what is the model of the light? So model of the light also adds ambience. Okay, but it would be in this formula only. So instead of LR, I can say LMR and MR. So the emission property of the material, the ambience of the light model into ambience of the model material. So if I set ambience of the light source to 0, still there will be ambience because light model ambience is there. This is attenuation. Light can decrease as per the distance. A spotlight effect, if we place a cone in front of the light, then depend upon the cutoff angle, the spotlight effect. Now ambience of the light into ambience of the material. Diffuse of the light, diffuse into the material. A specular of the light, a specular of the material. All factors if we add, plus, then plus. Okay. Okay. So this is the multiplying factor inside this. So again plus. So the ambience of the light, ambience factor, diffuse factor and shininess factor, whatever we get after addition, we have to multiply with the spotlight effect and the attenuation plus this, and then it becomes the okay. Now we can see there is a summation. This is number of the light sources. So if more number of light sources are there, then everything would get sum up. Okay. So in diffuse, this is L, means light, direction and normal. So we have to do dot. product, and similar to a specular component and the normal, we have to do dot. So light would be the brightest if dot means cos theta, cos angle. So cosine is maximum at the 0 degree. So normal of the material and light shows the light source direction. So it should be in the same direction. Means the dot should be 1. So it should be maximum. So material must be in material surface should be in perpendicular to the light, or material's normal should be parallel to the light. So this is the calculation. So we'll have lab session for all the calculations one by one, how it looks by changing what calculation. So it's pretty straightforward. Emission of the material, emission of the light model and material. Now for each light source, I equal to 0 to n number of light source, attenuation, a spotlight effect multiplied by all these factors, ambient, diffuse and shininess. For each we have to add, and that would become the vertex light. Means that would be the light that reaches the eye. Okay, so we have okay, so that is the material, that reaches to the camera. So finally the light should reach to the camera. So this, after adding this, if it crosses 1 means light has a boundary 1.0 in a float, then it would be kind of it would be curtailed to 1. So there is a boundary. So this is the idea. Now we demonstrated in. Now we will have a lab session. So in lab session, first we will go with the light source type, then light model, emission and ambience, diffusive and specular, then a spotlight. So this is the lab session we have kept for this. So in the current lab session, that is the first one, light source type. This one light source type. So this is the actual model of the lighting. So we can see that this is the camera, and camera is pointed towards minus z axis. This is the projection matrix, and inside the projection matrix we have a sphere, we have pyramid, and this projection is we can make it ortho or perspective, whatever comes to our need, and it. So far of the projection is 10, near is 1. This is our lab session, and minus 0.5 will place the local coordinate. At the local coordinate we draw these models, and from the local coordinate 1.5 distance we will have the light source. So this is the setup. So if I set 1.5 as a light source position in z direction, this would be the light source for the positional, whereas for the directional it would be infinite plus. It doesn't matter 1.5 or 4, it will be in z direction, and at infinite location the light source would be kept. So for the directional light, if I say the light position is 0, 0, 0, 0, 0, 1.5, light will be placed on 1.5, that is z axis, somewhere in the infinitely away, that is directional light, and this for the positional light it would be 1.5, it would be distance from the local coordinate, and so we'll show the directional light and positional light. Then we'll show the transformation, color emission, smooth shade model. Okay, so if it is a directional light, then light coming from the, so this is a perspective projection. So coming from the z axis, so this is the light source, but for directional this is far away, and we have a pyramid and we have a sphere. But if this is the positional light, then you can see that emission, its ambience is seen, because light is here. Because light is here. Since light is here, then it would behave like this. This part of the sphere is visible, this part is not visible. But here, in directional, light is coming from the infinite, here, from here. Light is going. So it would show like this. You can see shining is almost at the middle, because this is the perspective. In ortho, it will be exactly at the middle. So we have taken example from the ortho, from the perspective projection. In ortho projection, it will be exactly in the middle. That we will see. And light is seen from the infinite source. It is both are shining, we can see. But since this is a positional and we have only limited vertexes, one vertex is here and one vertex is here, and one vertex is here and one vertex is here, and one vertex is backside. So we can see only blue, because the color of this vertex is blue. These vertexes are not getting the light. So like this, it is red and it is green. But since it is positional near to the model, only this vertex is getting enough light. These vertexes are far and they are not getting the light. So light must reach the vertex. That is the idea. And from the right side, it is coming to this area. Back side is only ambience. So we have set ambience as blue. Okay. So this is the position and direction and type of the light. Now transformation, light can be rotated. Light is above now. It's possible, and it is showing the light from the top, like I have a chair. Okay. Color emission. So color emission and reflectance. So light does not have, light color is red and material color is green. So there is no color. Whatever color we are seeing is ambience color, because light model has white light. So it multiplies with the ambience of the material, and that comes to blue. So that we can see. Potentially there is nothing green here. So light is red. Material is green. So there is no lighting, because there is no calculation. It's 0. Light intensity test will make, like this is light. This is kind of bright light. So light also intensity we can change. It is a low bright light. And a smooth shade model. We can see that if camera is placed here, then light is everywhere. Or I can say if light source is placed as a directional, I can say this is a directional everywhere. But if light source is near somewhere and no vertex is receiving the light, then there is no light. This is positional light we have placed somewhere center, so that no vertex should receive the light. So vertex must receive the light. So this is the lab session that we will do. Okay, so we'll proceed with the writing the code. We'll create a directory. Dir OpenGL light. Okay, so it is empty directory. Okay, so we'll have a file that is gllight.py. From OpenGL.gl import star. Here you import star from OpenGL.glut import star. Now we'll import RE. I have a library file that is OpenGL utility, and it contains shapes, different shapes. Okay, so here we are. So from OpenGL, we will copy this file later. OpenGL util import pyramid util C and shape. Shapes will initialize how many shapes we support. So in shapes, first we will have a light cube. That light cube is a cube that show the cube where the light is. This is light cube. This is light cube. This is light cube. This is light cube. So light cube will show the location where the light is. Pyramid, sphere, chair. So all will have. As per the need, we'll comment it out and we'll enable whatever we need. We have a transformation. So it's like a hash in the sense dictionary, or X in shapes. Okay, so whatever shapes we have, for each shape there is an array. So that is the idea. Shape equal to initial shape equal to light cube. Pyramid equal to cube equal to chair equal to none. Okay, so there is a global rotate. We can global way we can rotate the angle. So I think we can include this. There is no harm. Global rotate angle equal to 0 and light type G equal to directional. So we will have directional light first, but we can change it on the runtime, and cube scale, how big the cube will be. So we can, if required, we can minimize, maximize the cube. So that is the idea. Now the crucial part, that is the init. So this is in OpenGL, init is a crucial part. So global is pyramid chair, GL clear color 0 0 0 0, GL shade model is GL smooth. This is what we are considering. So everywhere it is GL smooth. So GL smooth shading model. So this is what we are considering. GL enable GL lighting and GL enable GL light. So there can be many light source, I believe up to 8. So we are using light source 0, that is the first one. GL enable GL depth test, and pyramid equal to pyramid, cube equal to shape, and obj equal to. So we are using the object file that we receive from Blender. So Blender is a tool which generates the object file for the shapes what we draw there. Okay, so just for showing what is the Blender we are using. So this is a Blender. Like this is the cube, and we can save it. So generally we use triangular faces. So in edit mode, we have to go and face, make sure it is a triangular face, and then we can just export, and that's it, and we get the cube. So we are using Blender. So for the obj file is cube211.obj. We'll copy this cube. We have this file, and we have a chair also. So chair is also a shape of equal to chair.obj. Now we'll have a display. GL clear, GL color, buffer width, GL depth, buffer width. So every time we do the display, we don't forget to clear the buffers. So one is the color frame buffer and another is depth frame buffer. So both we clear. GL push matrix, GL translate, so translate F. So whenever so we are translating, pushing the item at -5. I think we have showed this. So if this is the camera, if this is the projection, then in the projection the local coordinate is 0, 0, -5. So this is what we are taking into the account. GL rotate, global rotate angle. So we have option of rotating everything along y-axis. GL rotate, global rotate angle. This is what we have taken, global rotate angle along y-axis. I think it should not be a tuple. For L shape, in shapes, GL push matrix, GL translate, if length of x greater than 3, else GL rotate x, for x in transformation of the L shape. So what we are doing is in the transformation, so we are keeping a transformation matrix for every shape. So whatever we are transforming for each shape, we are getting the transformation matrix, and in the transformation matrix, if it is length is equal to 3, means that is a GL translate, because for rotate we need 4 angle and then followed by like this. We have rotate, so angle and the 3 axis, where in translate only 3 axis. So if length is 3, then it is a GL translate, or otherwise it is GL rotate. So that is the idea. If L shape equal to light Q, now if the shape L shape okay, so if L shape equal to light Q, GL light FV GL light 0 GL position okay, so it is at 1.5 in Z direction and it is 0 if light type G equal to directional, else it is 1.0. Okay, so we have enabled light and we are setting the position for the light. So this is what we are doing. This is the position of the light. So position of the light is from the local coordinate, it is 1.5 in the Z direction. So GL light FB is GL light 0. For GL light 0, GL position is 0, 0, 1.5. 0 if light type is directional, S 1.0, that is the positional. I think it is straightforward. GL translate 0, 0, 1.5 and we'll draw GL disable, GL lighting, GL scale, cube scale G. So we will scale as per the, so we'll use floating point. So depth display, GL rotate F, translate F, rotate F, scale F, okay, so we'll proceed. Now we will draw the cube. So cube display, this is the API we are using, and color equal to 1.0, 1.0, 1.0, so it is white. Side color in the sense that what would be the color. So what we are trying to do is back side, it would be kind of yellowish. This is the back side, that is the back side of the cube. Front side should be red, like we can see that front side is appearing here, that is red. Back side is slight yellowish, so that we can identify it. So 0, 0, minus 1, so it should be red. 1, 0, 0.2, 0.2, and backs and the side near to the camera. So this is the side. So minus 1 is far away, and 1 is, that is minus z axis, 1 is z axis. So that we'd set 0, 0, 1, 1, 1, 0 point. It is kind of yellow. Okay. Now we will enable the lighting. We disabled because the cube would not be drawn nicely. Enable GL lighting. Okay. If L shape equal to pyramid dot display with the default argument, if L shape equal to sphere, GL material, GL front, GL ambient. Okay. So for the sphere, we are making sure that ambient is kind of blue. So 0, 0, 1, 1.0, GL material, GL front, GL diffuse. So diffuse we are making at green, GL material, GL front, GL specular 1.0. So specular is white, 1, 1, 1, 1.0. GL material F, GL front, GL shininess, kind of we can set 40. Glut solid is glut API sphere, and it is 0.5, 40, 32. These are latitude, longitude. If L shape equal to chair dot display, ambient equal to 0. So here ambient is green. Diffuse equal to, so its color of the chair is kind of red and blue, so I think that is cyan. Specular equal to, what would be shininess? So that is white, and shininess equal to 80, we will make 40. Okay, so we'll have a GL pop matrix and GL pop matrix. So this is the display. So this much is expected in OpenGL. So material color will place it as F. Real F. Okay, so we will have GL material, so all are float. So we are making sure that everything is float. Okay, so now we'll proceed to the reshape. Reshape we get width and height. So we'll have a global transformation what we had. GL viewport 0 0 and GL matrix mode is GL projection, GL load identity, GLU. So we are taking perspective so that at least depth we can, it should be visible. So 40.0 width by height, if width is greater than equal to height, else height by width 1.0 and 10.0. We can use ortho also. So probably we can type the code in experiment we can just enable it. So GL ortho minus 1.5 minus 1.5 into width into height by width 1.5 into height by width. So 1 to 20. If width is less than equal to h, else GL ortho minus 1.5 minus 1.5 into width by height 1.5 into width by height 1 to 20. Okay, so 20 we can change with 10. Okay, so this is the code. So in reshape we have GL viewport, projection load identity, GL perspective. Now, so GL perspective actually we are specifying as the projection. Now we will have GL matrix mode, GL model view, GL load identity, transformation equal to x. So if someone resizes the window, then it would kind of reinitialize it. Now we will have a keyboard. So keyboard is important because we will have animation through it. So keyboard gives key x and y. We will have global transformation because we are changing the transformation. Shapes, shape, global rotate, angle G, light type and Q scale, key equal to bytes. Key, so we make sure that key is byte. If key equal to BT, if it is a tab, then we'll change the shape. Shape equal to shapes. Shapes dot index, we find out what is the current shape and we just increment it by 1. shapes. So we move the shape. Okay. Util C dot. So in the util, we have a util OpenGL util package. So in that package we have keyboard. So that takes care of the key, and we pass the transformation for the shape, and it modifies the transformation internally. If key equal to P, then we will change it positional and directional. So probably I think we can make like this: light type equal to direction equal to positional if key equal to P, else directional I think this is the better way. Okay, if key equal to positional, light type G equal to positional, L if key equal to capital P, light type G equal to directional. Okay, so to print the states, in what state it is, so we'll have a BV. So someone wants verbose. So in util we have util. We'll show the util file. We have pretty print. In pretty print we have to show what we want. So we can say like we want shape equal to be printed. That would be shape. We want transformation equal to printed. That would be transformation matrix. We want light type to be printed, and that would be light type underscore G. We want global rotate angle to be printed, that is global rotate angle G. So that's it. Now we will have light cube size to be modified also. So if shape equal to light cube and R is set. So if it is capital or small c, key dot decode, because we want a string. If this is the case, then we'll have cube scale G equal to. So we'll increment by 0.05 if key equal to capital C, else we'll have max 0 x minus 0.05 for x in cube scale G. Okay, now we'll have global rotate angle. So this much pen is required in OpenGL code. So this is, I would say, minimum. Key equal to BG, else minus 10 plus 10 if key equal to BG, else minus 10 if key equal to capital G, else 0. गलत post display Okay, so we are done. Now I'll have all the formality. If it is a main, then what I have to do is glut init for glut functions. Then we'll have glut init display mode. Glut single we are using, glut RGB, glut depth, we'll do window initialize, window size 500, so like this. Glut init window position, that will be 100. Glut create window, my light code. So we'll call init function. Glut display func is display. Reshape func is reshape. Glut keyboard func is keyboard. Then we'll have glut main loop. Okay, so we are done with writing the code. Okay, so we'll browse it once before we actually start compiling, executing it. So we have OpenGL import, glut import, RE, and we have shapes. We have a transformation, shape equal to light cube, pyramid cube chair none, global rotate angle G 0, light type is directional, cube scale is 0. So in the init we have global pyramid because we have to instantiate, clear color is 0, smooth. So we are enabling lighting, light 0, depth test, and so we have done this lighting. So if I see, then this part first I have to enable. So specular and diffuse, they are by default, diffuse and specular, by default it is 1 and ambient is 0. Okay, no one stops at making it explicit, so that we can also do. Okay, now, so pyramid we instantiated, pyramid shape, we have a file called OpenGL util, from there we are getting this, and now we have display, so we clear the buffer, push the matrix, translate the local axis, we can rotate as per required just to show the procedure. Then we have L shape in the shape, GL push matrix. If it is a light cube, then this is the grammar. Here I can push in. So we are setting the position. No one stops at making me GL light FV GL light 0, GL specular, and that would be 1.1.1.0. So I can do like this, but this is anyway it is default. So these are anyway default. Okay, so GL position we set and directional it is 0. Translate disable lighting, then we draw the cube scale G. So cube scale G, is uh, the cube what we get. So we'll scale the Q, scale G as per, and finally we display the Q. We enable the lighting back. Now we have pyramid and pyramid display. If it is sphere, now we are setting the, so in the pyramid display mode, we are setting the GL material. For the sphere, we are setting here only. So two part, one is light part and one, this is the light emission and this is the light reflection. So that this will come as GL light V, GL light V, and this will come as GL material F. So that is the difference. So GL material FV in similar way. For every, so this is a kind of a state, means if, so this is for everything. I am drawing pyramid, so everywhere we need to change. Like if it coming to a sphere, then it will be, then same thing will be applied. If I don't have a color material tracking, that is another way we can track it and change it, but we are not using that. So this is the way it is. Then we draw the sphere. If it is chair, then we set ambient equal to, then diffuse equal to, then a specular equal to, and shininess equal to. Now we pop the matrix, and we flush it. In the reshape, now load identity GLU perspective. So that we have set. Model view, we have load identity. If someone reshapes, then shape is gone, all transformation matrix is gone. In the keyboard, we have light type and here shape would change. So keyboard is only one, so we can focus on a particular shape and we can transform it. So that is the idea. Keyboard handles the transformation, return the transformation matrix. Positional we can change, directional. If it is V, then we will make a pretty print. That is the idea. If it is a light cube, if shape is equal to light cube and it is a C, then light cube we would change, and then for global rotation we'll make it and glut read display. So we have glut init, display mode. So single, we are not using double. So coloring would be nice because we are not using high profile OpenGL speed. We are not taking that, so it should be okay. GL create window init display function reshape keyboard. So I think we are done. Light type. Okay, so it's okay. Okay, so we have only one file. Now, the way we showed, so we have other files also. So we'll copy called OpenGL utility here. We'll copy chair.obj here. We'll copy cube21 dot here. We'll copy obj loader here. Now we have these many files. So we'll say Python 3 GLLT. Okay, so if name equal to for x $67. Color is not defined. 42 substitute color. GL material, FV, GL front, GL diffuse. $48. Okay, we are getting. So we are getting all the steps. So I can print where what is my state. So I pressed V. Okay, so V is giving error. Local variable global rotate angle G reference before assignment. Okay. Global rotate angle okay, so I'll press V. Okay, so it prints the right now we are in the light cube and it is light cube pyramid sphere chair. Light type is directional, global rotate angle is 0. So probably I can change the pretty print little bit. Print transformation equal to light type equal to and angle G equal to. So this would be better. Okay, so I print V. Okay, so shape is light cube and transformation is for the light cube there is no transfer, pyramid, sphere, chair, directional, global. So now I have this. So right now it is light cube. So if I press Ctrl C, cube should come. Shift C, cube can become bigger. Cube can become smaller. Where the cube, I can press G to see. So cube is at a distance of 1.5. So here we are. Near is 1, far is 10, local is 5, we are at 5, and from here cube is at 1.5 distance. That can be seen. So cube is a little bit a distance from these entities. So we have drawn everything, sphere and chair. So I can say tab, then I can print where I am. So I am at a sphere. So if I press tab again, tab, and then if I print, so I am the chair. So I can bring chair pressing near N. If I press N, chair would. Okay. So since we have rotated the angle, so chair is moving towards the camera. So camera is on that direction. Okay. I can bring it back. Okay, so this is what initially we are getting. I can push chair down. I can rotate chair. along x-axis also, along y-axis also. So this is the chair, and along z-axis also. Okay, so we'll move. So I'll show the code of the OpenGL utility. That is the promise. So OpenGL util. So OpenGL util has a class utilC, and it provides a function like normalize, get normal vector, display. So in the display, we set the ambience, specular, shininess, diffuse of the shape, and this is GL triangles. So the mode of the draw is GL triangle. That has to be okay. Get buffer is if I receive buffer from the obj file, where to trim to get the interleaved buffer. This is to get the color and get the vertices, the normal texture. Then it has a keyboard. So keyboard we are using, and then it has pretty print, and it has a shape. So whatever shape we want, then it initializes the obj file and vertices, normal, indices, and then it has a display shape also, which calls util.c, and pyramid we have separate init file, and vertices we have hard coded, indices, color, normal, and finally we have display for the pyramid separately. So this is the architecture of OpenGL utility file. We have obj file. Obj file we have downloaded. It's a obj loader. Otherwise, from the Kiwi resources, we use resource find, and then we have debug write print. So this is kind of modifying the print. Okay, so we'll proceed with the laboratory. So in the laboratory, first we have lab session, we have directional, then we have positional, and we don't have chair now. So what we can do now is we will open the GL light, and in the shape we will have pyramid. We don't want chair, so we'll, and we can let execute. Okay, now we have, this is a directional light. It is coming from infinite distance. Now we'll select sphere. Now mode is directional sphere. I press 2 times tab, it came to sphere. Whatever key now I press, it will go to sphere. So idea is that so we'll make sphere move, right? Now it can be seen that light is falling on the sphere. So sphere, it is going right side because of the GL perspective. If I use GL ortho, no one stops me doing that. We will now try in ortho fashion. So I'll comment this. So this is ortho projection. So this projection, so we are taking now ortho, otherwise we are using perspective projection. So now in ortho, if I take the cube right, Okay, so we can see that the shininess or a specular is at the center. We can try both. So the old one. So right side is perspective and left side is ortho. And if I take, so there is a difference. So in perspective, the directional light changes because perspective is not the uh, a typical cuboid. So that is the difference. We'll go with the perspective. Okay, and if you see the keyboard, so keyboard is like LRDUN, left, right, up, down, and XYZ is rotate along XYZ. And if we see here, if I press tab, then shapes would change. So whatever shape is in current kind of focus, so that would take the keyboard. So that is the idea. So from the OpenGL util package, we import util C shape. So util C contains the keyboard for the left, right, or something like that. And in the keyboard, P and capital is for positional and directional. The way it is, we print the current state, and light Q we can kind of make it big, small. Now we'll come to original discussion. So directional light is placed at infinite, whereas positional is 1.5. This is what the design is. So we will take out the sphere from here and we'll place somewhere here. So we can do something like this. Idea is that we'll take out the sphere from this place. First we'll place it here, then we'll take it right. So that is the idea. Take here, then to the right. Now we'll see the difference. So cone would be kind of straight in the minus z direction, and this would be in the positive x direction. So this we will get. Okay. I'll recheck what is the condition. Okay, so we'll use GL perspective and comment the GL ortho. So that is the idea. Now, what I will do, I press 2 tab. If I see the situation, I have selected a sphere, and transformation for the light cube, pyramid and a sphere is empty. There is no transformation. And now I can bring a sphere in front, and if I see the condition, it is 1.2. It is 1.4. Now it is 1.5. So 1.5 means we brought the, so cube is now here. cube is here. Now I'll get it to right side. So this is directional, means light is positioned. So if I see the code, okay. So in the code we have placed it 1.5, 0, 0, 1.5, but 1.5 for the directional light is along 1.5, 0, 0, only Z component is there, positive is there. So on the positive side, it is at infinite distance. So I can prove that first. I can say left, 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 far, 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 far. Now I can bring so this is the light cube. I mean, I can kind of rotate it. So this is the light. Now I'll take the sphere in the front, in the near. It came above the light, still it is glowing. This proves that light is not there. The light cube is drawn here at 1.5 and sphere we are bringing beyond this. So light is here. So this side should be shadow, but it's not shadow. So light is not there. In direction, light is at infinite distance. It will cross the projection matrix if I make more near. Okay, so this is what it is. So gone. So light is not there. I'll see the situation where it is. It is 2 point. So sphere is 1.34. So it is 1.2. Now I can make it right. And I would change it to positional now. So I shall press P. This is positional light. This is directional light. This is positional. In the positional light, the light is at 1.5. Light is here. So no one stops me doing the same experiment. So where I am? I am at a sphere only. So I can say left, 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 gone. There is no light. This is ambience. Blue I have set. So if I say far, okay, so light is appearing and appearing and appearing. So this is positional. Whatever we see the area where there is no light, this is the ambient light. Whatever we see the green part, this is the specular light. This is the diffuse light. And this white light is the specular. And at the center what we see the highly shining, that is the shining amount. Okay. Next thing, so if we see so directional light, it is at infinite distance. And in the pyramid, there is 5 vertices. 1 vertices, 2 vertices, 3 vertices, 4 vertices, and 1 vertices is behind the scene. So there are 5 vertices. In the 5 all vertices, whatever receives the light, that should glow. Okay. So I think I can show it later because that is not right now. So now the next is so if I see the position and direction. So direction we saw, where is the direction? So direction is omni and light in the directional is positioned at infinite distance, whereas in the positional it is at nearby. Okay, and we can see that it's only blue, whereas this should be. Now if I move the light up, this is positional light. Now red vertex is getting the illumination. So vertex, whatever is getting the illumination, color of the shape would be like that. It doesn't matter what is in between, pixels or fragments or its area or surfaces, only vertex. If vertex receive light, then only blue is receiving. Other became. So this is the concept. So let's move. Now we have transformation. So light can be transformed. Light can also move. Like I can move the light. It's clear? Light is on back side. So pyramid has no light, and this one is ambience is blue. So this is what it is coming. Okay. So light can be transformed. I can show on the chair also. So I have another example with the chair. I have a chair, and if I see the constituency of the chair, okay, so if I see the chair display, so chair is ambience is blue, red, green. Ambience is green. Diffuse is cyan, and specular is white. So if there is no light, it should look green. Otherwise, diffuse is cyan and specular is white. Shininess is 40. So this is how it should be. So diffuse is white. As we can see, I can bring the Q, and this is positional light. This is directional light. So positional light, this is the front part. So diffuse is coming into the picture. Otherwise, this is the actual color. Okay, I can rotate the Q along x-axis. Okay, so light is not reaching this part. So this is the ambience. Light is reaching nicely here. So this is white. Otherwise, this is the color. Okay, so this is positional light. So I'll keep on. Okay. Now, as light is more focused, the specular part is more prominent. Now it is completely white. Okay. I can rotate the light. I'm sorry. Okay, when there is no light, it is green. This is the ambience. Okay, this is the actual color. But if light come near more, then this is the specular and shininess. So what I want to show is that light has transformation, object has transformation, object has transformation. Light has transformation. Light can go up, it can go down. I mean, there should be a difference, I believe. Okay. Light can go right. Okay, difference is coming, but it's not highly visible. Probably we can, okay, difference is there. Okay, so right can move up, down, left, right. Light can rotate. Okay, so transformation is possible in light as good as it is in any model. Okay, now we have color emission and reflection. Okay, so whatever color we have for the light, if that color is not doesn't belong to, so I think, okay, if light is only red, reflection is only green, then as per this model, this will be 0, this will be 0, and this will be 0. So there should be only ambience. Now I am going to, okay, so we'll bring back sphere and we'll see. So we'll change the light as per the design. Okay, so light diffuse is only red. So the light coming from the source is only red. Sorry. And the sphere color, you see the sphere color, the diffuse is only green. Red is emission and reflectance is green. So it should not do the magic. So I am going to show it now. So we'll make it a sphere. We'll try now. Okay, so there is no light. This is directional and this is positional. Still only ambience is there. Now I can rotate it. Okay, I am not, I think I am pressing R. So I'll press Y to rotate along Y axis. Okay, I think I should show the cube. This is the light. So no green. I can change the color of the light. Now instead of red light, it has green component also. Red component is there, green component is there. Let's try. Wow, this is what we wanted. Now it's there. Now I am free to, I can show the cube. I can rotate now. So this is the light model. Okay, we'll try if really it becomes complete black. So we'll make it again 0 as green, and in the ambience we will make it 0. So there is no ambience, it is black. It is really black. Okay, so if there is no ambience, so I can show the cube, and if there is no ambience, so a specular is there because I have set a specular as white. Otherwise, there is nothing. So white shininess is coming because there is a specular one, and here in the sphere there is a specular one. Okay, so I'm not going to change it. So we'll keep it as, and here, so light also will make it 1. Okay, so this is the idea. Now we'll proceed to next example. Light intensity. So color is dependent upon the light intensity also. So intensity of the light. So how much intensity? So if light is 1, then it is pure green. If it is half, then depend. I can change here, I can change there, anywhere, because after, at the end, multiplication happens. Okay, so I'll change at material first. So in the material, diffuse is 1 point. Okay, so this is full, and for the solid sphere, diffuse is 0.5. We'll try. Oh, so if color intensity is different, then also color changes. I can try through light, or I think it should be okay. It will work in that fashion only. Okay, now if there is a light that is at the not at the vertex, then will it be black? Here, so if we need very nice color, then we have to go for tessellation, and there should be many triangles. We are using triangles, so we have only 4 vertices. Okay, I can show the cube. We'll go with pyramid. So I'm checking if we have reverted back. Okay, it wouldn't matter for pyramid though. It's okay. So this is our pyramid. I want to glow it even nicely. No one stops me. Making it diffuse as 2. Okay, more shining. Now we'll have positional light. Okay, let make it directional so that at least it should be. Or positional, then we have to go far. So if I say near, the light will come near, and more nice the I can remove the light. So this is positional light. Now I can just rotate it and I can show. This is a pyramid. This is a pyramid. This is a pyramid. Okay, so we'll come to the. Okay, so if I resize, then everything comes to normal because this is the code. If I resize, after load identity, all transformation matrix are reset. Now, this is the. Okay, so okay, I think positional. Okay, so we are at pyramid. Okay, now this would work. Okay, now this is the light source. I can rotate the light source. I can move up. Looks nice. Let's move near to the pyramid. Gone. So light is directly falling. It is so near to the pyramid that vertexes are not receiving the light at all. So light is in front of the pyramid, but it is nothing. So this is OpenGL. If I move up, then red vertex is getting the light and little bit green and blue. If I move down, sorry. Okay, if I move down, nothing. So this is OpenGL. I can bring near. So light is coming near to us. If I press far, light is going towards pyramid. There is. So light is going away. Okay, so we showed all the experiments. In a smooth shade model, light must fall on the vertices. Light intensity changes. We can change the light intensity. Color emission is color based. The color component in the light must have the color what material want to reflect. Transformation happens in light also. Transformation happens in directional light also and positional light also. Both. So, if I bring at the beginning it's directional. This is directional light. So, if I rotate, so just for showing but this is not exact position of the light, but still if I rotate, directional light also rotates. To prove it better, I can bring in another guy called chair. So this is directional light. Okay, this is positional light, this is directional light. So just for simplicity, now if I rotate, directional light also rotates. Even though it is at infinite distance. This is positional light, this is directional light. Okay, now the directional light is at minus z axis. It is at z axis at infinite distance. We can see that chair is completely illuminated. If I bring the chair near to us also, then chair would be visible. If I make it P, positional, okay, so ambience what we can see mainly. Okay, so we covered directional and positional light, position and direction. So whatever position we set, that position is actually positional light, and for the directional, this position axis it takes. Transformation we showed that light can also move. Color emission, light of the color and light of the material matters. Light intensity, we can change the intensity of light through material and through light both. And it's a smooth shading mode. In a smooth shading model, vertices should be illuminated. So we can make it kind of tessellation, and we can make it many triangles. So there will be many vertices, and it would be illuminated in better way. Okay, so we'll move towards next exercise. That is light model emission and ambience. So that will be emission of the material that we will see now. Light model emission and ambience.